Hello, I am Seppo Niemi-Colvin, and welcome to Invariance of Knot Lattice Homology Part 2. As a reminder from our first video, the main theorem we're working towards is that knot lattice homology is invariant for knots on which it is defined, i.e. generalized algebraic knots. We spent most of the first video talking about lattice homology and building that up so that which was the corresponding three-manifold invariant. This time, we're going to discuss lattice homology and give its context, give the plan for proving invariance, which has two parts: find moves that preserve the knot and get you between pieces of the knot, and showing invariance under those moves. So let's get into knot lattice homology. Given a disk bundle over the sphere, there is a natural knot to look at in the boundary, which is the boundary of the fiber. When this occurs in a plumbing, we can represent it as an unweighted vertex hanging off of that sphere. In the case of lattice homology, we weren't concerned with all plumbings. We were just concerned with the negative definite ones, which had an algebraic interpretation. And that will be true here as well. When the plumbing is negative definite, we get a generalized algebraic knot, which is a link of a normal complex surface, singularity, and a curve. So here we have a surface, complex surface, and here's a curve inside it with a singularity. And the curve may be more or less more singular than the surface even. We have that this over here is the three-manifold link of singularity. And this, which is where the curve meets the link of singularity, is the generalized algebraic knot. As a note on the term generalized, this is because algebraic knots are generally assumed to be in S3. But generalized can have more complicated links of singularity that they are sitting in. So last time, we had the broader context of Haggard-Floer homology informing what we were doing, because lattice homology was attempting to compute it. In this case, we are then going to be working with knot-Floer homology as our broader context. Knot-Floer homology was developed by Osvath and Szabo and simultaneously Rasmussen as a bigraded Z adjoining U V module, where U and V are formal variables, each with a -2 graded in a different grading. Each variable is keeping track of one presentation of the three-manifold, and the lattice gives information on how these two presentations differ. It tells us lots of useful things about the knot, such as the genus, which it just detects on the nose, or rather you can detect it using knot-Floer, and concordance info, which isn't quite as precise in the same sense that it was on the genus side, but still gives you, for example, lower bounds on the four-ball genus. You also have the surgery formula, which lets you recover Haggard-Floer, the Haggard-Floer homology of Dane surgeries on the knot, where you rip out a tubular neighborhood of the knot and glue it back in differently. So it is a very useful invariant. However, it is as hard to compute as the Haggard-Floer homology of the ambient three-manifold, because it contains inside of it two presentations of the three-manifold. So it has to be at least as hard as having one presentation. And as such, a lot of known computations are in the three-sphere. There's a lot of computations, but a lot of them are in the simplest three-manifold, so you can keep the three-manifold contribution to the difficulty simpler. Knot lattice homology Well, this was developed by Peter Roosevelt, Andras Lipschitz, and Zoltan Szabo. Like NOT-FLUR, it is a Z-adjoint UV module and is bi-graded. And U and V are each keeping track of one filtration from lattice homology for the three manifolds. You then have two filtrations going on. To achieve this, the two, we can consider our original one and a translation. And this translation is being done with a second cohomology class, which is in particular the Poincare dual of the fiber that we took the boundary of to get our knot. And let's zoom in on this picture to talk about the example. So in grading 0, 0, by grading 0, 0, we just have this one vertex because that's the only place where this magenta ellipse and this blue ellipse overlap. So we'll just, that is, the homology of that is just a single thing, which we can put there. And if we go to -2, 0, which means making the magenta ellipse, the ellipse corresponding to the first grading, bigger, we pick up this here and the edges between those. So that's still contractible. So we get a single thing here, and we'll have a horizontal arrow pointing to pick up the U. Now for the magenta, now let's do magenta ellipse. We made that bigger to get the -2, 0. Let's make the blue ellipse bigger, but keep the magenta ellipse the same size. Look at 0, -2. Similar thing going on, but these will always have some amount of symmetry. And pick up there. Finally, we can look at -2, -2, which will be the intersection of both the magenta and blue ellipses, and get here. Still contractible. And in fact, we will get that this pattern just continues onward, always contractible all the time, because this is a fancy unknot, which has homology Z-adjoint UV. Like with lattice homology, it's hard to get very complicated examples in 2 dimensions, practically impossible. However, you can in 2 dimensions see an example of what might happen to help jog intuition for what more complicated things could appear. For example, what if the translates didn't overlap at all? Let's do there and there. Make these -2 and -2. So 0, 0 is then empty. It has trivial Heyerdahl homology, not Heyerdahl homology. So many homology theories flowing around. And we can then look at 0, -2, picking out this, and -2, 0, picking up that, both of those contractible. And in fact, as we move on to -2, -2, it fills in like before. And this is a more complicated module, and looks in fact similar to the trefoil. The relation between knot lattice and knot FLUR is more shaky than the relationship between lattice and homology and Heyerdahl FLUR, though hopefully it should be the same, just less explored. Still, we do know that knot lattice homology is going to be the same as knot FLUR homology if the ambient 3 manifold has no U torsion in any spin C structure. This is a a common enough thing in Haggard Fleur, or rather at least a common and important enough thing that has a name as an L space. And lattice homology also shares various formal properties with not Fleur. Let me actually, such as the surgery formula. In fact, not lattice homology was defined to be precisely what it needs to be to make the surgery formula work, while also picking up other similarities with not Fleur. A lot, however, still remains unknown. For example, genus, concordance, or more general concordance stuff need to be looked into. However, given the computational successes of lattice homology, there's hope that not lattice can be a useful tool. Let's now move into the plan for proving invariance. To start off with, despite all similarities, a proof for invariance had not existed before. This is usually one of the first things one checks with a new calculation based on a topological object, but it is so big that it is easy to get lost in the trees and not be able to see the forest that ties it all together, while having the benefit of being very explicit compared to not Fleur and Haggard Fleur. And I will state also that here invariance is up to homeomorphism, sending one embedding to the other of S1 to the other. And to show in this sort of invariance, we will first find a set of moves that preserve the knot type and get you between any two presentations of the same knot. These are like the Reidemeister moves, but for graphs. So the Reidemeister moves are moves that you can do to get between any two projections of the same knot, and therefore useful for showing invariance of things that are defined based on knot projections. We're going to need to have a similar set of things because our invariant is based not on a projection, but on a graph. After we have these set of moves, we'll then need to show that not lattice homology is preserved under these moves. In particular, by finding a chain homotopy equivalence relating before the move and after the move. Let's cover the moves. They're going to be regarding blowing up a point. Blowing up a point algebraically replaces a point with all the complex lines through that point. So here we have a point, and then here's some complex lines. And when we blow up, that point becomes a copy of CP1, parameterized all the lines going through it. And if we approach the point through it this way, we'll end up at there. But if we approach here, which are separate things based on the angle of approach, and if this looks sort of like the picture earlier from regarding disk bundles, that is not a coincidence, because we will then have a disk bundle over a sphere with Euler number 1 sitting inside our blown up surface. This is smoothly a connect sum with CP2 bar, where bar is the orientation reversal of the complex projective space. The key point to take away with this that makes it so useful, though, is that this happens on the interior of the 4 manifold and therefore does not change the link. In terms of graphs, this has several different ways it can show up. And these all depend on where the point is. For example, this is our graph of a knot. It's actually the trefoil. And here's a different one, which is based on a generic blowup. Here our point is not in the preimage of the singularity. And it's away from basically anything interesting that's going on. The next piece is blowing up a vertex, which is where the point is on exactly one surface in the preimage of the singularity. And you can see here, we went from this -3 to a -4 connected to the new sphere. New sphere, often called the exceptional sphere. This edge is indicating how they're now entangled because of how the choice of point to blow up. And the lowering can be thought of as will be smoothly the same thing as if you blow up a generic point and then moved it in. And so there's a change of basis that changes the self-intersection as you go along. The other, number 3 is blowing up an edge. So we've blown up this edge here, which then moves those two spheres apart because they were intersecting at different angles, and then those are now different points on the new sphere, exceptional sphere. And our exceptional sphere is now entangled with both of those. As said, due to change of basis and moving it in, we then get those lowering by 1. Finally, we have stuff that we can do to the unweighted vertex. The main important thing being blowing up the edge connecting the unweighted vertex to the rest of the graph, shown here. This behaves sort of similarly to blowing up an edge, but also sort of similarly to blowing up a vertex. And the work to show that not lattice is invariant under this move was actually done previously by Ozlov, Lipschitz, and Szabo in their paper that introduced not lattice homology. Finally, we have all these moves that do preserve the knot type. Seeing that these moves are sufficient to get between any two representations of the same knot requires mimicking proofs found in Walter Neumann's The Calculus for Plumbing. This is the paper that included the statement that the homeomorphism type of the link determined the algebraic singularity type, and it was through these sorts of things. Walter Neumann's The Calculus for Plumbing also contained a statement regarding general knots and plumbings, with proof left to the reader. Needing to merge these two together, though, was not given before, and as I said, required mimicking and merging the ideas between those two proofs. Finally, we need to show invariance under these moves. Each new blowup adds a new sphere, E, the exceptional sphere, to the plumbing, and thus a new dimension to our lattice. If there were no filtrations, we could collapse this dimension away without worry. So in particular, we could choose this, a representative that looks similar to our pre-blowup lattice, and send everything while moving it up in that direction, then that direction again, there. These arrows represent a homotopy done in steps because that will be useful when things get more complicated. In that we can't just choose a random layer and send it there. We need to do it in a way that respects both filtrations that we have going on. Well, let's see. If we only had one filtration given by our height function h, we would carry every element in a column towards the element achieving the column's maximum. And well, turns out this also works in the presence of the translated height function, so long as one makes the right choice in columns where the maximum is achieved in 2 places. In particular, the steps of the homotopy, so long as the height function is changing and actually increasing along those steps, will still work afterwards, due to the fact that, well, it is a translation by V0. V0 is small enough that it won't change it too much. The problem is just when you have 2 things matching. And let's pull this up bigger to talk about it in context. For example, this edge, the minimum of -8 and -2 is -8. The minimum of -6 and -2 is -6. The fact that -6 is strictly bigger than -8 means that we can indeed move this edge towards the bottom edge without it respecting both filtrations, which will pop up in a moment. However, the minimum of -6 and -4 is also -6. So the problem is we don't know whether we should be moving this down or that up. However, this actually is enough to prove invariance because we just need to check the second filtration, and one of those two directions will be allowed. As such, let's check what's happening. Here we had a -8 before, and actually it's the same calculation to have a -8 again. Here we had a -6, and now we have a -4 and 0. That's a -4. So if anything, we're even more allowed to move this down, taking in the second filtration we've added of the translator of the first. Furthermore, here we had a -6 to start with. Now we have a -2 and 0 and -2. So what we didn't know before, now we see that -2 is bigger than -4, so it should be going down. And that is enough for the proof of invariance in general. However, I will make some comments regarding the special case of rational homology spheres that we can see in this case, which is that if we look at all of these question marks, we might be asking ourselves, which direction is that going to end up? And we go here and we're looking at the down, another down, 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 down. And this is a pattern that I'm going to talk about here with the special case. For rational homology spheres, I found a way to recursively compute the difference of H across two opposing faces, which is what we need to know to see if we can homotop something in one direction or the other. And the recursive piece is that, say this is a cube supported on everything, we want to know the difference in the direction given by this vertex, because our vertices are giving directions that our lattice is happening in. Well, recursively, we can get some contribution from this vertex that depends only on this vertex, plus a contribution that looks at what is happening on these two smaller cubes that are supported in smaller directions. And then looking at how what the difference is across opposing faces based on that direction up top and that direction over there. And this can continue until we can reduce it down and compile all these different directions that things are tilting. The important piece here is that these recursion lets me effectively track how calculations change when our height function is translated by V0. In particular, V0 will affect the contribution from this vertex, which is then affecting the difference across here, which then affects the difference across here. And this cascade can be, and tracking when things can change and the direction in which things are changing can be consolidated to say that the choice of up or down at question marks depends only on the parity of the graph theoretic distance from V0 to E, which was in our original case up top, and thus does not depend on which cube question mark you were looking at. As a reminder, our theorem is that knot lattice homology is invariant for knots on which it is defined, i.e. generalized algebraic knots. With invariance, other inquiries into knot lattice will be more meaningful. I plan to, in the write-up of this into a paper, check that this chain homotopy equivalence preserves relevant maps similar to those in the larger knot-floor package. And these constructions in this proof, such as the chain homotopy and dot recursion, may be useful in further computation.